Every programmer has faced the frustration of code that simply refuses to work as expected. You've written your logic, compiled your project, and yet, the application behaves unpredictably or crashes entirely. This common scenario can be incredibly time consuming. This video will guide you through mastering debugging in C Sharp, transforming moments of confusion into clear paths to resolution. We'll equip you with essential skills to efficiently identify, understand, and fix issues within your C Sharp applications. To achieve this, we'll explore 5 essential tools: breakpoints, the watch window, the call stack, debug, log, and assertions. Each plays a crucial role in unraveling code complexities. First, let's delve into breakpoints, a fundamental debugging technique that allows you to pause your program's execution at a specific line of code. It's like hitting a pause button, letting you examine everything behind the scenes. A breakpoint is essentially a deliberate pause, giving you a snapshot of your application state at that precise moment. It freezes execution, allowing you to inspect variables, memory, and the flow of control. Consider this simple C# for loop intended to sum numbers, but it's producing an incorrect result. This subtle error is common and tricky to spot, making it a perfect candidate for debugging. Without debugging, identifying the exact flaw can be challenging. Let's set a breakpoint within the loop, specifically on the line where the sum is being updated, to observe its behavior during each iteration. When we run the program in debug mode, execution halts precisely at our breakpoint, allowing us to inspect variables and understand the program's state. This pause is critical for understanding miscalculations. Once paused, you gain control with core debugging commands: step over, step into, and step out. These allow you to navigate through your code line by line, or jump into and out of method calls, giving granular control. Step over executes the current line of code and moves to the next without diving into method calls. This is useful when you trust a method and don't need to examine its internal workings, allowing quick advancement. Step into allows you to dive inside a method call on the current line, executing its code line by line. This is essential when you suspect an issue might be originating from within a called method, tracing execution. Conversely, step out executes the remainder of the current method and returns to the calling method. This is a time saver when you've stepped in and realized the bug isn't there, quickly returning to a higher level. For more precise control, use conditional breakpoints. These only pause execution when a specified condition is true, saving you from manually stepping through countless iterations. You define the condition. This is incredibly useful for debugging loops or large datasets where you only care about a specific iteration or value. You can set a breakpoint to trigger only when a loop counter I equals a problematic number. Next, let's explore the watch window, a powerful companion to breakpoints for inspecting variable values in real time. It provides the lens to observe your data, indispensable for diagnosis during paused execution. Continuing with our for loop example, with execution paused at the breakpoint, we can add variables to the watch window. This allows us to monitor their values as the program progresses, providing immediate feedback. Observe how the values of I and sum change with each step through the loop, revealing the exact point where the calculation goes awry. You can see the sum accumulating incorrectly, pinpointing the bug's origin. This dynamic inspection helps pinpoint the source of the bug with precision, revealing logical errors not immediately obvious from static code analysis. It transforms abstract code into observable behavior. A pro tip for the watch window: you can actually edit variable values on the fly during a debugging session. This allows for immediate experimentation and hypothesis testing without needing to recompile. This allows you to test different hypotheses without restarting your entire debugging session, saving valuable time. You can change an input value to see how it affects the program's flow or correct a variable temporarily. Moving on to the call stack, think of it as a breadcrumb trail of function calls, like a stack of plates. It records the sequence of method calls that led to the current point of execution. Each time a method is called, it's added to the top of the stack. When it finishes, it's removed. This LIFO structure accurately reflects the execution flow, showing active methods and their order. Let's use a new example with nested function calls. Main calls process data, which then calls validate input. This demonstrates how methods can delegate tasks, building up the call stack. We'll set a breakpoint inside the validate input method, the innermost function in our nested call structure. This allows us to pause execution at the deepest level and examine the call stack. When execution pauses, the call stack window clearly displays the hierarchy: main at the bottom, then process data, and finally validate input at the top. This shows the exact path your program took. Double-clicking any function in the call stack will instantly switch the editor's context to that function's code. This allows you to quickly jump between different parts of your application's current execution flow. This feature is invaluable for understanding the flow of execution and tracing back to the origin of an unexpected error. If a bug occurs deep within a nested call, the call stack helps you navigate upstream.
Next, we have logging, a simpler yet highly effective debugging method using console.writeLine or debug log. This involves strategically placing statements to output messages or variable values to a console, providing runtime insights.
Logging involves printing information directly to the console at various points in your code. These messages can indicate program flow, variable states, or specific events, acting as breadcrumbs. When the program runs, these messages appear in the output window, providing insights into variable states and execution flow without interrupting. This non-intrusive nature makes logging suitable for continuous monitoring. Logging is particularly useful in long-running processes, multi-threaded applications, or environments where a full debugger isn't available. In these complex scenarios, logging becomes the go-to method. The key is to use meaningful and clear log messages. Avoid just printing raw numbers. Provide context. A well-crafted log message can save significant time by immediately conveying relevant information. For example, instead of just console.writeLine, use console.writeLine. This descriptive message immediately tells you what the number represents and its logging point. Finally, let's discuss assertions, specifically debug. Assert, a powerful tool for declaring assumptions in your code. Assertions are statements that you believe must be true at a certain point, helping catch logical errors. An assertion states that a certain condition must be true at a specific point in your program. If this condition evaluates to false during debug mode, the assertion will trigger, indicating an unexpected state. If the condition is false, the program will halt in debug mode, alerting you to an unexpected state. This immediate interruption prevents further execution with invalid data, making it easier to identify the root cause. Consider a function expecting a non-null object. We can add debug, assert, at the beginning. This ensures valid input, preventing null reference exceptions later. Running this with a valid object, where myObject is not null, the program proceeds normally without interruption. The assertion passes silently, confirming your assumption about the object state. However, if we pass a null object, the assertion dialog immediately appears, stopping execution and displaying the custom message. This clearly indicates a critical assumption violation, pointing to a potential bug. Assertions are for catching impossible situations and programmer errors during development, not for handling expected user errors. They are internal checks for code integrity, distinct from input validation. A crucial pro tip: debug, assert statements are automatically compiled out of release builds. This means that when you deploy your application to production, these assertion checks are removed, ensuring no performance overhead. This means they don't impact your production performance, making them safe for development time checks. You can liberally use assertions during development to enforce invariants and catch bugs without affecting end users. We've covered breakpoints, the watch window, the call stack, debug, log, and assertions. These 5 powerful tools form the cornerstone of effective debugging in C#, providing a comprehensive toolkit. Integrate these powerful techniques into your daily coding workflow to become a more efficient and confident C# developer. By mastering these tools, you'll spend less time frustrated by bugs and more time building robust applications. Happy coding! May your debugging sessions be swift and your code always run flawlessly. Thank you for watching, and we hope this guide helps you on your journey to becoming a C# debugging master.